Hi everyone. Our project is about predicting daily COVID-19 rates in US counties. The COVID-19 pandemic continues to affect countries around the world. In the US, COVID cases are now at an all-time high, and states have implemented various levels of restrictions to try to control these rates. Our plan is to evaluate how different county features affect the daily number of COVID cases. Using these significant features, we want to predict the number of COVID cases in a county. Our datasets come from the US Census, various Kaggle sets, a Kaggle competition, and USA Facts. Our features include county demographics such as race, ethnicity, population density, and political affiliation, state policies including school closure dates and gathering ban dates, mobility rates, and previous number of cases. Our label is the daily number of cases in a county. We combined 7 datasets from these various sources into one CSV file with 350,000 records and 32 features.
So when pre-processing our data, we first converted dates into number values, which correspond to the days between March 1st and July 13th of this year. A challenge that we faced was that we had missing values in our demographic and mobility files. So what we had to do was to use the k nearest neighbors inputter to fill in the missing values, and we used 13 nearest neighbors for k. We then created a new feature by computing the average number of cases over d days. In our preliminary results, we used d equals 7. We then split our data into 70% training data and 30% testing data, and normalized the data with standard scalar. Finally, we did dimension reduction with PCA, keeping 95% variance with 24 components. We built 3 different models: linear regression, decision tree regressor, and random forest regressor. And we wanted to compare our results against an existing model from Pandemic Central, which reported an R-squared value of 0.997. We first did linear regression, and we also got an R-squared value of 0.997. The coefficients for the linear regression model can be seen in this graph, where the Asian population feature had the largest absolute value by far. The large negative coefficient suggests that counties with large Asian populations experienced lower COVID cases. The most positive coefficient was the previous number of cases, so a large number of previous cases in a county indicates that there will be a large number of future cases. We were also quite surprised that mobility rate and population density did not have significant coefficients, because we expected these features to be correlated with higher COVID rates.
We then implemented a decision tree regressor and a random forest regressor. Using Grisser's CV, our best decision tree hyperparameters so far are max depth of 11 and minimum least size of 1. For the random forest, the best hyperparameters we have so far are nest size of 50, max features of 6, max depth of 10, and minimum least size of 3. For both of these models, we found that our predictions without using PCA resulted in better R-squared and root mean squared error values. Out of all 3 models, we found the highest test R-squared of 0.999 and lowest root mean squared error of 87.32 from the decision tree. This R-squared value is slightly better than that of the Pandemic Central model, with an improvement of 0.002. For future plans, we will try other data preprocessing methods in order to reduce variance because PCA did not improve our model performance. We plan to use the Pearson correlation heat map to drop features before running our models again. We will continue doing more hyperparameter tuning. For linear regression, we will use lasso ridge regularization and tune lambda. We will further tune max depth and minimum least size for the decision tree and random forest, and nest size and max features for the random forest. We also want to apply the ensemble method to the 3 models we have implemented by using significant features from the linear regression as the features for the decision tree regressor, and features to subset from for random forest. And lastly, we're thinking of using future COVID-19 growth rate as our label instead of number of cases. To predict the future number of cases, we can multiply our growth rate by the previous number of cases in order to get the number of future cases. Thanks everyone for listening.